Welcome to our educational video on deep learning. Throughout this journey, we'll delve into the foundational aspects of deep learning, providing clear insights and practical applications. First, we'll answer the fundamental question: what is deep learning? This sophisticated field of machine learning uses neural networks with multiple layers to automatically discover intricate patterns in vast amounts of data. But why is deep learning so critical in our modern era? Deep learning powers advancements in technology, from enhancing image and voice recognition to revolutionizing industries like healthcare and finance. You'll see its pivotal role in current and future innovations. We'll provide a broad overview, starting with the basics and gradually building up to more complex concepts. We'll cover neural networks, different types of architectures like CNNs and RNNs, and explore their real-world applications and challenges. Join us as we uncover the world of deep learning. By the end, you'll have a comprehensive understanding of this transformative technology and how it's shaping our future. Let's get started on this exciting educational adventure. Deep learning is a subset of machine learning, distinguished by its use of neural networks with many layers. Unlike traditional machine learning algorithms that rely heavily on pre-programmed rules and feature extraction, deep learning automates much of this process. It does so by learning the representations needed for feature detection and classification directly from raw data. This allows deep learning models to achieve higher accuracy on complex tasks, such as image and voice recognition. Understanding this distinction is crucial as we dive deeper into the intricacies of deep learning. As we move forward, you'll see how this powerful technology is applied and how it continues to evolve. The concept of deep learning dates back to the 1940s with the development of neural networks. Early pioneers like Warren McCulloch and Walter Pitts laid the groundwork with their models of neural activity. In the 1980s, the introduction of backpropagation by Geoffrey Hinton and others was a pivotal milestone, enabling neural networks to learn from their errors. This breakthrough ignited waves of research and experimentation. However, it wasn't until the 2000s, with the advent of powerful GPUs, that deep learning truly began to flourish. This resurgence allowed for the training of complex neural networks on massive datasets, propelling the field to new heights. Today, deep learning is a cornerstone of artificial intelligence, driving advancements in areas like speech recognition, computer vision, and natural language processing. As we move forward, you'll see how these historical developments have shaped the landscape and set the stage for even more revolutionary breakthroughs. Welcome to the core concepts of deep learning, where we unravel the mechanics of how these powerful models function. At the heart of deep learning lies the neural network. Picture it as a complex web of interconnected layers, each filled with nodes akin to neurons in the human brain. These nodes, or neurons, are the fundamental units that process information. The structure of a neural network is hierarchical. The first layer, known as the input layer, receives raw data. This data is then passed through multiple hidden layers, which transform and refine the information step by step. Finally, the output layer presents the result, be it a classification, prediction, or any other specific task. The magic happens through the connections between these layers, represented by weights. These weights determine the strength and direction of the connections between nodes. But how does the network learn? This is where the training process comes into play. During training, the neural network adjusts its weights based on the error between its prediction and the actual outcome. This is typically achieved through a method called backpropagation, where the network learns to minimize this error iteratively. Over multiple iterations, the network fine-tunes its weights, enhancing its accuracy and performance. This process transforms a basic neural network into a sophisticated model capable of discerning complex patterns and making informed predictions. As we move forward, you'll see how these neural networks are applied in various domains and the types that cater to different needs. In deep learning, several types of neural networks are commonly used, each with distinct structures and applications. Feed-forward neural networks are the simplest type, where information moves in one direction, from the input layer through hidden layers to the output layer. Convolutional neural networks, or CNNs, are primarily used for image and video recognition. Their unique architecture is designed for tasks such as image classification, object detection, and clustering. Recurrent neural networks, or RNNs, are tailor-made for sequence data, like time series or natural language. RNNs are vital in applications such as language modeling and speech recognition. Each type of neural network plays a crucial role in the diverse landscape of deep learning, offering unique advantages depending on the specific use case. As we move forward, you'll learn in more detail about each type and their specific functionalities within the broader scope of deep learning. Feed-forward neural networks are the simplest form of artificial neural networks. Information flows in one direction only, from the input nodes through any hidden nodes and finally to the output nodes. This straightforward structure makes them the foundation upon which more complex networks are built. Feed-forward neural networks process input data and pass it through successive layers until it reaches the output stage, where a prediction or classification is made. They are often used in tasks such as pattern recognition and classification problems. Understanding the basics of feed-forward neural networks is crucial before diving into more advanced topics. As we move forward, you'll see how these networks lay the groundwork for more sophisticated architectures, such as convolutional and recurrent neural networks. Stay tuned to explore these fascinating structures and their unique functions in the world of deep learning. Convolutional neural networks, or CNNs, are the cornerstone of modern image and video recognition techniques. They excel at tasks like classifying images, clustering them by similarity, and recognizing objects within scenes. But what sets CNNs apart? The secret lies in their unique architecture. Unlike traditional neural networks, CNNs utilize convolutional layers designed to process grid-like data, such as an image. These layers detect various features in an image, like edges, textures, and patterns, by sliding filters over the input data and capturing relevant information. CNNs are instrumental in medical imaging, providing accurate and early diagnoses by scrutinizing millions of medical images. In self-driving cars, they identify and classify obstacles, ensuring safer navigation. Even in social media, CNNs power facial recognition systems, enhancing user experiences by tagging friends in photos automatically. Next, we'll explore another revolutionary type of neural network, recurrent neural networks. Stay tuned as we continue this educational journey into the world of deep learning. Recurrent neural networks, or RNNs, hold a unique place in the world of deep learning. Unlike traditional neural networks, RNNs are specially designed to recognize patterns in sequences of data. Imagine trying to predict the next word in a sentence, or identifying speech. These tasks involve understanding the context and dependencies within a sequence, which is where RNNs excel. Their structure allows them to consider previous inputs in the sequence, creating a memory of sorts. This ability makes RNNs particularly powerful for tasks that involve time series data, natural language processing, and speech recognition. In language modeling, for instance, RNNs can predict the next word in a sentence by considering the words that came before it. In speech recognition, they can understand and transcribe spoken language by recognizing patterns over time. Understanding the function and structure of RNNs enriches our knowledge of how deep learning can interact with sequential data effectively. Up next, we'll explore the steps involved in training deep learning models, including data preparation, the training process, and evaluation. Training a deep learning model is a meticulous yet rewarding process. It begins with data preparation, the foundation of any successful model. Here, data is collected, cleaned, and pre-processed to ensure quality and relevance. This step includes tasks like removing duplicates, handling missing values, and normalizing data. Once the data is ready, the training process commences. This is where the model learns by iterating over the data multiple times, adjusting its parameters to minimize errors. It's a dynamic phase involving optimization algorithms like gradient descent to fine-tune the model's performance. After training, the model's effectiveness needs evaluation. This involves testing the model with a separate dataset to assess its accuracy, precision, and recall. Evaluation metrics like confusion matrix, F1 score, and ROC curves come into play here. They provide insights into how well the model performs on unseen data, identifying potential areas for improvement. As we move forward, you'll see how these fundamental steps are applied in various deep learning models to achieve remarkable results. Understanding these steps is crucial as it sets the stage for tackling more complex challenges in the realm of deep learning. Stay tuned as we delve deeper into the nuances of model optimization and real-world applications. As we delve deeper into deep learning, it's crucial to understand the common challenges faced during model development. Overfitting is a significant issue where the model performs exceptionally well on training data but fails to generalize to new, unseen data. On the other hand, underfitting occurs when the model is too simple to capture the underlying patterns in the data, leading to poor performance both on training and new data. Another major hurdle is data quality. High-quality, clean data is essential for building effective deep learning models. Ensuring the data is accurate, relevant, and abundant can greatly influence the success of the model. Addressing these challenges requires a careful balance of model complexity and robust data pre-processing techniques. As we move forward, you'll see how these challenges can be mitigated through thoughtful practices and advanced techniques, paving the way for more reliable and powerful deep learning models. Deep learning has transcended theoretical concepts and found its way into a multitude of real-world applications. In healthcare, it revolutionizes the field by analyzing medical images with unmatched precision and accelerating drug discovery for critical treatments. In the financial sector, deep learning detects fraudulent activities, predicts market movements through algorithmic trading, and manages risks more effectively. Meanwhile, the realm of autonomous vehicles depends heavily on deep learning for object detection, ensuring that these vehicles can recognize and safely navigate their surroundings. As we move forward, you'll see how deep learning's influence extends even further, reshaping industries and driving innovation to new heights. In healthcare, deep learning is changing the game in medical image analysis, offering more precise diagnoses than ever before. With its ability to analyze complex patterns, it identifies abnormalities in images with unprecedented accuracy. This doesn't stop at imagery. Deep learning is pivotal in drug discovery, predicting the effectiveness of new drugs swiftly and reliably. Researchers can now sift through vast data sets to uncover potential treatments more efficiently, accelerating the journey from lab to patient. Additionally, predictive analytics, powered by deep learning, forecasts patient outcomes, helping doctors make informed decisions. It analyzes numerous variables to predict disease's progression, patient readmissions, and overall healthcare trends, ultimately improving patient care and operational efficiency. As we explore further, you'll discover even more profound transformations driven by deep learning. In the dynamic world of finance, deep learning has become a powerful tool. One key application is fraud detection, where advanced models identify unusual patterns in transactions, helping to prevent financial crimes. Another groundbreaking use is in algorithmic trading. Here, deep learning models analyze vast amounts of market data to predict trends and execute trades at lightning speed. Additionally, it plays a crucial role in risk management, assessing potential financial risks and advising on strategies to mitigate them. As we move forward, you'll discover how deep learning is transforming other industries, such as autonomous vehicles and beyond. Autonomous vehicles represent one of the most transformative applications of deep learning technology. By leveraging complex neural networks, these vehicles can perform object detection, identifying and classifying elements in their environment with remarkable accuracy. This ability to see and understand surroundings is crucial for safe and efficient operations. Navigation systems in autonomous vehicles rely heavily on deep learning algorithms, integrating real-time data to make informed decisions, ensuring optimal routing, and adapting to changing traffic conditions. Advanced safety systems can predict potential accidents by analyzing patterns and behaviors that precede collisions, enhancing safety by adjusting speed or altering course. As we move forward, you'll see how these technologies are revolutionary, setting the stage for a future where autonomous vehicles become an integral part of our daily lives. Stay tuned as we delve deeper into the practical applications and groundbreaking advancements in this field. As we reach the end of our journey, it's time to gaze into the future of deep learning. Emerging trends, such as unsupervised learning and reinforcement learning, are paving the way for revolutionary advancements. The potential impact of these cutting-edge technologies spans various fields, from healthcare and finance to autonomous vehicles and beyond. Future research continues to push boundaries, exploring new methodologies and applications once thought impossible. The promise of deep learning is immense, with innovations that will reshape industries and redefine technology's limits. As we continue to explore these frontiers, the possibilities are truly limitless. Thank you for joining us. Stay curious and keep learning. In this video, we delved into the fundamentals of deep learning, exploring its rich history, intricate workings, and myriad applications. We began by defining what deep learning is and distinguishing it from traditional machine learning. We traced its historical milestones and broke down how neural networks operate. We examined different types of neural networks, such as CNNs and RNNs, and discussed their unique use cases. We then looked at the steps involved in training these models and the common challenges faced during development, like overfitting and underfitting. We showcased the real-world applications of deep learning in fields such as healthcare, finance, and autonomous vehicles, highlighting how it's transforming industries. As we wrap up, we encourage you to continue your journey in unraveling the complexities of deep learning. The future holds vast potential, with emerging trends and ongoing research paving the way for exciting innovations. Thank you for joining us on this educational journey. Do like, share, and subscribe to stay updated with more insightful content on deep learning and beyond.